Okay, hello everyone. Welcome to another part of the Basics of Quantum Gravity School. This school is organized by the International Society for Quantum Gravity, or ISQG, and also by the ISQG Young Researchers team. During this week, Astrid Eichhorn is going to introduce the asymptotic safety scenario for quantum gravity and also discuss some of its phenomenological implications. Astrid is a professor at the Center for Cosmology and Particle Physics Phenomenology at the University of Southern Denmark. She has received her PhD at the University of Vienna and has been a postdoc at the Perimeter Institute for Theoretical Physics, as well as the Imperial College in London. And before moving to Denmark, she has held a junior professorship at the University of Heidelberg. Astrid is one of the leading researchers in asymptotic safety and its connections to particle physics, astrophysics, and cosmology. But Astrid has also great expertise at the intersection between asymptotic safety and other quantum gravity approaches, such as causal set theory. She's an experienced lecturer, and we are very much looking forward to her lectures. They will take place today, tomorrow, and on Friday, and they will also be recorded and later uploaded to YouTube as we already started the recording. If you have questions, you can either type them in the chat or raise your hand, and we will also have plenty of time for discussions after the lectures. So with that, thank you, Astrid, for accepting our invitation, and please feel free to share your screen and start when you're ready.
Thanks, Johanna, both for the invitation and also for the kind introduction. Indeed, it's a great pleasure to be giving this introduction to asymptotically safe quantum gravity. And I think you should now be able to see my screen, and I think you can also see the cursor, right?
Yes, we do.
All right, great. So before I get started with this first lecture, let me just say that my preferred way of doing this would be for you to basically interrupt me as often as possible with questions that you have. If there are any questions at any point, then just type them into the chat. I will try to keep an eye on the chat, or just raise your virtual hand or interrupt me. So I'm very happy if this becomes as much as a Q&A as possible. All right, with that said, let me first set the stage by asking a very general question, and namely what we actually know about the fundamental building blocks of nature. And what we know to date is actually encoded in two theories: in the standard model of particle physics on the one side, and in general relativity on the other side. We also know that both of these theories are actually incomplete, and they break down at certain points, and so we need to go beyond in order to really understand the fundamental, the microscopic building blocks of nature. And I'll briefly review how and where these two break down, so that we can get an indication of what is the type of theory that we need to develop next in order to go beyond the current status of our understanding. And I'll be starting with the status of the standard model of particle physics. So here is the collection of particles in the standard model, and this figure here shows the couplings in the standard model that parameterize the interactions, and it shows them as a function of the energy scale. And the status pre-LHC, so some sort of 12 years ago or so, was that we knew the standard model at these energy scales of around 100 GeV or so, and it worked quite well at those scales. But we also had a very, very clear indication where the next scale of new physics had to be, because from measuring the masses of the weak gauge bosons, you can actually infer that if there is a Higgs particle, then its vacuum expectation value has to be 246 GeV. And if there isn't a Higgs particle, then the electroweak sector runs into a problem at a very, very similar scale, so somewhere below the TeV scale. And so therefore, before the LHC was switched on, there was a very good, very robust theoretical understanding of the scale of new physics, which was basically at LHC scales. And then indeed, of course, there was new physics right at these scales, and the new physics turned out to be the simplest possibility of them all, namely just a Higgs that has to be added, or that was already part of the standard model. And now what is really exciting about the Higgs discovery, I mean, beyond the discovery itself, of course, is what the discovery is now telling us about where the next scale of new physics actually has to be. So where does this understanding that we have of the building blocks of matter now, where does this actually break down? And for that, you have to actually take a look at the mass of the Higgs that is related to this vacuum expectation value, and then is multiplied by a factor of this coupling, λ4, that parameterizes the quartic-Higgs self-interaction. And that is actually quite interesting because it just depends on the scale very, very weakly until at very large energies or very, very small distance scales, it actually starts to diverge. And this divergence, the so-called Landau pole, or beyond that, the triviality problem, that actually signals that this is a scale where new physics has to exist. And you can see that it's actually quite a high scale. It's actually a very, very trans-Planckian scale. And the fact that this scale of new physics is actually so high, that was not a guarantee before the discovery of the Higgs, because it turns out that there's only a sort of very, very narrow range of Higgs masses where you can, in fact, extend our understanding of the degrees of the fundamental building blocks of matter until these very high scales. And that is because if you make this quartic coupling somewhat larger at low energies, so you make the mass of the Higgs somewhat higher, then this divergence here sets on much, much earlier, and you run into the so-called triviality problem. And so if you want the standard model to be consistent for a very large range of scales, this narrows, or this bounds the range of allowed masses from above. And then there's also a bound from below, because you see that the quartic coupling here dips into a negative regime. And if it becomes truly negative and doesn't become positive again, then that would be instability of the vacuum, a very significant theoretical problem. And that bounds the masses of the Higgs from below. And so you see that if you change the mass of the Higgs by just changing this quartic coupling here, then you end up with a very different situation where the mass of the mass scale that is associated to the new physics could actually be much, much lower. So you can see that if you make the Higgs mass somewhat higher, then you can easily end up with the prediction that new physics has to exist at, let's say, 10 to the 6 or 10 to the 7 or so GeV. But that's not the situation. What the measurement of the Higgs mass at this scale is actually telling us is that we could be facing what has been called this desert scenario, where the standard model really is basically everything there is for a very, very long range of scales. And then new physics that significantly interacts with the standard model only comes in beyond the Planck scale. There's, of course, the unresolved question of what, for instance, the dark matter could be, but there are scenarios where you can just have dark matter explained by various elementary particles that don't couple strongly to the standard model and don't change this picture very much, or actually even just talk to the standard model gravitationally. And I see that there's a question in the chat. So has the scaling of the Higgs mass been observed at the LHC? So I'm assuming that the question refers to whether the running of this quartic coupling has been measured at the LHC. And I don't think that that is the case, because I think to measure this quartic coupling with much more precision, you would actually want something like an E+ E- collider. But I'm not an expert on how to do these measurements of the Higgs quartic coupling. As far as I know, the running of that has not been tested over the range of scales of the LHC. What the main thing for this talk here really is that now post-LHC, we're in a totally different situation from pre-LHC. So pre-LHC, we had a very clear idea that new physics had to be right around the corner. Now, post-LHC, we actually have the indication that the new physics scale is somewhere far, far beyond the Planck scale, which means that actually quantum gravity would kick in much earlier. And that then brings me to the status of our understanding of gravity, where, of course, the last decade has been super exciting, with finally getting both indirect and more direct observations of black holes, both through gravitational waves and through black hole shadows. And of course, these observations are so far very well compatible with the GR predictions. They are also compatible with these predictions within quite significant systematic uncertainties. So the agreement between theory and experiment is only within systematic uncertainties that you shouldn't ignore. So these are not necessarily as precise tests of general relativity as, for instance, we have in the weak field regime. So indeed, the situation is as follows. So here in this figure, you see sort of two ways of thinking about strong versus weak gravity. One of them is the curvature scale, and the other is the value of the sort of gravitational potential. And then gravity has been tested quite well in the regime where the gravitational potential is relatively low, for instance, by various solar system tests, and also by observing the gravitational field, how it acts on atoms. But then what is newer is these tests really at high values of the gravitational potential, where we are really testing strong field gravity. And where now we observationally see that black holes exist. But of course, theoretically, we know that as we go really deep into this strong field regime and deeper into a black hole, at some point we're encountering the breakdown of GR through the curvature singularity that GR black holes actually have. And what that is telling us, that these objects that we are observing, even though currently the observations are compatible with GR predictions, we already know fundamentally that these cannot be black holes from general relativity, that general relativity ultimately breaks down in the description of these objects because of the curvature singularity that it predicts. From this setting here, we don't have a very clear indication for what the scale of new physics is. From the agreement between the observations and the theory, you can exclude that there is a new physics scale that is very, very large, that would be that predicts strong modifications on the order of a sort of curvature radius of a black hole, but there is no clear prediction for what the scale of new physics should be. And so overall, when we look at the status of our understanding of the fundamental building blocks of nature, we have an understanding that already reaches quite far. And really the indications that we have for the breakdown of GR and of the standard model of particle physics is pointing us to new physics only setting in at or beyond the Planck scale, where quantum effects and gravity become important. There are, of course, open questions in particle physics, but there is no theoretical consideration that would sort of uniquely motivate a particular scale of new physics where we would expect new particle physics to come in before the Planck scale. And so this then means that if we want to make progress in understanding the fundamental building blocks of nature, then the next thing to do is to understand really the quantum properties of gravity and then its interplay with matter as well. And so this is what I'm planning to do in these lectures. So roughly the plan is as follows. I'll start this first lecture by reviewing what the problem is with the perturbative approach to quantum gravity, and then explain how an asymptotically safe approach can overcome that problem, and I'll introduce the sort of the main concept behind asymptotic safety, and I'll also review some mechanisms how you can generate asymptotic safety. And that will then bring me to asymptotically safe quantum gravity. I'll talk about the tools that can be used to search for asymptotic safety in gravity, and then I'll present the evidence that exists. And then the plan for tomorrow roughly is to then take one step further and go beyond just the understanding of quantum theory of gravity and understand quantum gravity together with matter. And then probably for Friday, depending on how many questions you ask today and tomorrow, then probably Friday we'll get to the topic of what is the understanding of black holes that we have in asymptotic safety, how do they differ from black holes in GR, and I'll give a critical discussion of the main method that is used to build asymptotic safety inspired black holes, and I'll also discuss their properties. And I will also be highlighting some of the open questions and challenges, but also I'd be very happy to include any questions that you, the audience, raise. So if during my discussions on these topics, there are things where you would like to see more discussion of, or aspects that I've not highlighted in what I'm going through here that you would like to see discussed, then I'd be very happy to receive your questions on that and put them into the lecture that I've planned for Friday. So please feel free to let me know if there's some other aspect that you would like to see discussed. All right, so for now, let me start with the problem of perturbative quantum gravity. So I'm working within the path integral formalism for quantum gravity, which means that any observable is calculated from the integral over all metrics weighted with a quantum mechanical phase factor, so that configurations either interfere destructively and are excluded from the path integral, or interfere constructively and give some contribution to observables. And the starting point is the Einstein action for gravity, which is just based on the Ricci scalar and comes with a coupling, the Newton coupling that parameterizes the strength of gravitational self-interactions and also the coupling of gravity to matter. And then in a perturbative approach, you would start by evaluating the classical contribution to an observable and then introduce or evaluate the quantum contributions in a loop expansion. And then at one loop, you're already encountering divergences. And these divergences take the form of the following four operators. There's a divergence that is just related to the determinant of the metric. And that would tell you that you would have to introduce a cosmological constant as a counter term to this action. Then there is a divergence that takes exactly the same form as the action that we've started with. And so this means that this divergence can be absorbed in a renormalization of the Newton coupling. And then there are also divergences that are higher order in the curvature terms in R squared and a Ricci tensor squared term. And these would mean that you have to introduce new counter terms that were not part of your original action. Now, at the one loop level, there's a sort of way around this, at least if you're in pure gravity without a cosmological constant and without matter, because then the Einstein equations tell you that both R and R mu nu are actually zero. And so this means that on shell, these two counter terms vanish. Even in that setting, however, as you then go to two loops, there's a new counter term, the Gorov-Zaniotti counter term, that is basically the Riemann tensor cubed, that is not of the form of the original action. So it has to be introduced as a new counter term. And there's also no way to argue that you can set this to zero, because even the vacuum Einstein equations don't generically give you a vanishing Riemann tensor. And in fact, you expect that this pattern continues based on the superficial degree of divergence in perturbative gravity. You expect that whenever you increase the loop order L, the superficial degree of divergence of the diagrams goes up. And that then ultimately implies that at every loop order, there are new interactions. So basically at every loop order, there will be two more derivatives or another power of a curvature tensor that comes into the counter terms that you have to introduce. And so technically this is known as perturbative non-renormalizability, but what that technical term actually means is that the theory loses predictivity, because each of these counter terms here comes with a coupling in front of it, and that coupling is a free parameter. There's no way to determine it from theoretical considerations. And so therefore, you have to make an experiment in order to measure it. And so the higher you go in loop order, the more experiments you would actually have to do in order to just pin down the free parameters of your theory. Or looked at in a different way, if you would make a prediction for, I don't know, the scattering of gravitons or some other prediction at a given loop order, then likely going to next higher loop orders, there would be more counter terms that would contribute to the same observable, and that would just spoil your prediction because they come in with a new free parameter that enters the prediction. And so that's really the problem of perturbative quantum gravity. It doesn't, however, mean that general relativity and quantum physics can't be reconciled, as one so often hears. That statement is plainly wrong. They can actually be reconciled as an effective field theory. So in an effective field theory, you assume some form of naturalness, which basically means that you assume that all of the couplings that appear in all of the interactions in the theory, all of these couplings can be written as a dimensionless coefficient that is of order 1, and then just the same mass scale, which for gravity you would choose to be the Planck scale, by the appropriate power that is set by the dimension of the term. And if you make this assumption, then the higher order interactions in the theory are subleading for everything that happens at energies that are below the Planck mass. And so in this way, you can, for instance, then predict or calculate the quantum gravity corrections to something like the potential between two point particles. However, what the problem, of course, is that if we want to understand what happens to quantum gravity in the sort of most interesting regime close to and above the Planck scale, where quantum gravity effects are no longer small, as they are here, the problem then becomes that we truly have to confront this loss of predictivity, and there is no way around having to confront these infinitely many free parameters and having to find a way how we can get rid of basically infinitely many of them so that we can get back to a theory which has just a finite number of free parameters. And one potential solution or one pathway to a solution to restore predictivity is to demand that the theory has more symmetry. So whenever you impose a symmetry on an action, then that generically relates couplings to each other or just sets couplings to 0 and thereby reduces the number of free parameters. So a very simple example is just a real scalar field theory that has no internal symmetry. So there's just a real scalar field phi. And then the allowed interactions, for instance, include all powers, all positive powers of the scalar field, and of course also various derivative interactions and so on. Then if you require more symmetry, so for instance, a simple symmetry to require is an internal Z2 symmetry, which just maps the scalar field to its negative, then you immediately cut down the allowed number of interactions with 0 derivatives. You immediately cut them down to half as many interactions because only even powers of the scalar field are allowed. And you could say that there is a gravitational example that sort of follows this idea of making a theory more predictive by demanding that it is more symmetric, and that is supergravity. Just to show you that idea works in the sense that there is more predictivity if the symmetry is higher. Here's a table from a recent review of the status of supergravity, and the interesting case to focus on is d equal 4 dimensions. And then n equal 8 is the maximum amount of supergravity that you can require. And then it actually turns out that most of the counter terms that you have in perturbative quantum gravity at low loop orders, they are actually not supersymmetric, and so they are excluded. And so the first counter term actually comes in at quite high order in derivatives. And so it only kicks in at 7th loop order. And currently in 4 dimensions, there is no calculation that shows whether or not this divergence actually exists. There is a sort of equivalent, in some sense, calculation where you change the space-time dimensionality to 24/5, and then the same counter term already shows up at 5th loop order, and there is a corresponding divergence. However, in this table, you can also see that there are some unexpected cancellations going on in supergravity, namely expected counter terms don't have the corresponding divergence. So supergravity removes more counter terms, or sort of there's more symmetry than one might naively expect. However, generically, the expectation still is that the theory ultimately has an infinite number of free parameters, even though the number of counter terms is reduced significantly. And so we need to think in a somewhat different way about symmetries in order to really restore predictive power to quantum gravity. And the way to do so is by not requiring that symmetry at the classical level, as we usually do, but instead thinking about how a symmetry could only emerge at the quantum level. And this will lead us to the idea of asymptotic safety. And the symmetry that will be important here is scale symmetry. So scale symmetry basically says that once you understand the system at one scale, you understand that at all other scales, it doesn't change anymore. And just from the simple explanation, you can sort of see why this would be an attractive paradigm for quantum gravity, because it would mean that if we can make sense of quantum gravity, for instance, at the Planck scale, then we immediately understand gravity at all higher energies or lower length scales because of the scale symmetry. And so the hypothesis that I'll be discussing today is that the quantum structure of spacetime is described by a theory that is scale symmetric, but in a very particular way, namely by becoming asymptotically safe And that means that scale symmetry only emerges at the quantum level. Before I go there, let me just briefly discuss that scale symmetry really is also a concept that is already ubiquitous in science. It makes an appearance in various examples in mathematics and sort of self-similar systems or fractals. There's also lots of approximately scale symmetric examples in the natural world. Then scale symmetry also is crucial for the theory of phase transitions. So whenever you have a second order or higher order phase transition, then at this phase transition, the correlation length in the system diverges and the system doesn't have a particular typical length scale anymore. And you can see this in this example here of the Ising model. So just a model of a spin that of many spins that can either be pointing up or down. And if you imagine that the black is just whenever a spin points up and white is spin pointing down, then you see that below the critical temperature, you have sort of an ordered phase, all of the spins pointing up. Above the critical temperature, you have sort of small islands of magnetization. And you can also see that they have a sort of typical size. So you can see the correlation length that the system has, and it's clearly not scale symmetric. But then at the critical temperature, the system becomes scale symmetric because if you look at these sort of islands of one particular magnetization, either up or down, you can see that they occur in all different sizes or at all different scales. And so this is how this phase transition point is actually characterized by scale symmetry. And then lastly, scale symmetry is also important in particle physics, for instance, in the strong interactions, where we see here the scale dependence of the coupling of the strong interactions that asymptotes towards zero as we go to very, very high energies. And once it reaches zero, then it also reaches a regime of scale invariance. And now the idea is that we want to realize scale symmetry in a quantum field theory. So that means in the presence of quantum fluctuations. And generically, what happens in the presence of quantum fluctuations is that you get a non-trivial scale dependence of the couplings, just as you see it here for the coupling of the strong interactions. So the couplings generically become what is called running couplings, and the scale dependence is described by a renormalization group flow. So scale symmetry is then non-trivial to achieve. You can, however, achieve it if you just switch off all of the interactions in the theory. This is basically a way of switching off the effect of quantum fluctuations. And in this way, you can reach asymptotic freedom. It corresponds to what is called trivial fixed point of the renormalization group. That option is not an option for gravity. That is just rephrasing the statement that gravity is perturbatively non-renormalizable. There is, however, a more non-trivial option to get scale symmetry, and that is not just switching off the interactions, but actually balancing different interactions in such a way that you achieve scale symmetry, so the couplings become independent of the scale, but you do that at finite values of the interactions. And so this is what I call quantum scale symmetry. It's a scale symmetry because the system doesn't change as you change the scale anymore, but it's achieved at the quantum level in the presence of quantum fluctuations, which actually are crucial in order to generate such a scale symmetric regime. And this is what is then known as asymptotic safety, and it corresponds to a non-trivial or an interacting renormalization group fixed point. And now, of course, the crucial question is how this idea of enhanced symmetry in this non-trivial sort of quantum way, how this actually restores predictivity to the theory. And before I discuss this, let me very briefly pause to see whether there are any questions. Okay, there don't seem to be any questions right now. So how do we get predictivity from asymptotic safety? So I think it's probably intuitively more obvious that when we are in this regime where we have asymptotic safety or scale symmetry, that is something that we cannot achieve at arbitrary values of the couplings, but that we need particular values for the couplings so that the interactions can sort of balance out. And I will talk a little bit more about that in the next slide. And so the values of the couplings are therefore fixed in the UV. But then, of course, if we look around us, we clearly see that there are different scales in nature. So we don't live in a scale symmetric world. And so there has to be some transition scale at which the system then departs from the scale symmetric regime, and we have some scale dependence that drives the couplings to other values. And it's less immediately obvious that asymptotic safety actually also generates predictions for most, not all, but for most couplings in this regime. So there's just a few free parameters, namely those linked to the so-called relevant couplings. And I'll explain the mechanism for that in detail. But what the upshot of that is that by imposing quantum scale symmetry in the UV, predictivity is restored to the theory because the values of the couplings are fixed in the UV regime, and also the values of all but the relevant couplings are fixed at all other scales. So let me talk about these mechanisms in a bit more detail so you understand where the predictivity comes from. So where do we get the predictivity in the UV from? Well, we get that because we require quantum scale symmetry, which means that the scale derivative of the couplings, and those we call the beta functions, so they are just the dimensionless scale derivative of the couplings, we require that those vanish. That is what characterizes scale symmetry. And that actually, if you calculate all of the beta functions of the couplings, then this requirement just translates into a system of coupled algebraic equations. And generically, of course, there's at best a finite number of real zeros that such a system has. And I see that there's a question in the chat. So the question is, if I understand correctly, whether asymptotic safety could also give a different behavior, namely an exponential dependence or an oscillatory dependence on the couplings, on the scale. Is that the question? Or I'm not sure I'm understanding the question correctly. Maybe you can also unmute and ask your question. Okay. If you don't mind to rephrase, then I'll just take a look at the question again. I'm not sure I'm understanding what you have in mind right now. So then let me continue with the explanation of where the predictivity in the UV comes from. So because we are looking at this system of algebraic equations and we're looking for its zero, then we are guaranteed to find a zero when all of the couplings vanish. That is just physically, if we put all of the interactions to zero, then the theory cannot change with scale because there are no interactions that would drive a scale dependence. So there's always the free fixed point. But besides that, there's at best a finite number of real zeros. And typically, in theories, we just have no more than one interacting zero if there is one at all. And so you can also see this in this plot here. So this will be actually two of the gravitational couplings. And you can see that if you just go to sort of generic values of these couplings somewhere, then there's always a scale dependence that is indicated by these arrows here. And there's only one very particular point where both couplings take particular values and they can balance out in such ways with the other terms in the beta function that indeed here the scale dependence vanishes. And so this is where predictivity in the UV comes from. And you can also see that in these type of tables. So this is an example where we're looking at a gravitational action already. I'll come back to that in more detail later, which has 8 couplings of powers of the Ricci scalar. And you see that requiring asymptotic safety actually fixes those couplings to unique values. And so this is how the theory becomes predictive in the UV in the regime where you have the asymptotically safe fixed point. And now let me come to this question where predictivity actually comes from in the infrared, because this is much more non-trivial. And
sorry,
yes,
I may have a question
concerning go ahead.
Last slide. Hi, sorry.
Yep.
So is there, this might be a very general question, but do you have any strong feelings about the exponents being complex conjugates? Because for this Einstein theory, you have this spiraling behavior of the running.
Yeah.
Is that because that's very specific to gravity, isn't
it? So it's something that is definitely more unusual for other interacting fixed points. I don't think there's necessarily anything problematic with it.
Okay.
It's also the case that this can change depending on the sort of level of approximation in the calculation.
Sure.
So this is not something that we sort of know for sure must occur for gravity.
Okay.
But yeah, I'll actually come back to the critical exponents also in a bit later.
Thanks. Thank you.
And then there was the question in the chat. Okay, now I understand the question. So the question is, what is sort of the advantage of asymptotic safety over sort of other behaviors of the couplings? For instance, if there is sort of maybe an exponential dependence, so that the coupling only diverges at infinity, or that it sort of oscillates forever. It's of course a sort of really different physics, in the sense that in one case you do have scale symmetry fundamentally, in the other you don't. But I would say the main advantage of asymptotic safety over sort of other behaviors of couplings really is that it allows you to restore predictivity to the theory, not just in the fixed point regime in the UV, but also in the infrared. And so by requiring asymptotic safety, it's really a very strong requirement on the theory, because it generically means that even in the presence of infinitely many interactions, you end up with just a finite number of free parameters. That is what I would say is the main advantage of asymptotic safety, that it makes a quantum field theory quite predictive. All right, so that wraps up the question in the chat. So let me now go to this question of where the predictivity in the infrared actually comes from. And to understand that, we need to remind ourselves that what quantum fluctuations do is they either screen or they anti-screen interactions, which means that as we go to larger length scales or lower energies, the interaction either becomes lower because it's screened, so it decreases, or it becomes stronger because it's anti-screened. And in the standard model, we have examples for both. So in quantum electrodynamics, the beta function starts with a positive term. And because the beta function is the scale derivative in energy scales, this means that as we go to lower energy scales, so larger distances, the value of the coupling decreases. And so this is sort of the screening behavior, or the screening impact of electron-positron fluctuations, or generically fluctuations of charged matter. And there's sort of a heuristic intuitive picture behind that, where you imagine that there is a charge sitting there interacting with a field, and then you have virtual electron-positron pairs that appear and disappear in the vacuum. And if you look at the chart with a certain resolution scale that corresponds to 1 over this energy scale, then of course you will see some accumulated effect of all of the sort of electron fluctuations here that screen that charge, and that enhances as you go towards larger and larger distances. And then in quantum chromodynamics, you have the opposite sign that basically comes from the self-interactions of gluons, whereas of course QED has no self-interactions of photons. And this negative sign here means that as you now go towards lower energy scales or larger distances, then the coupling increases. And this is what you see in this plot here as well. So the Q is basically the same thing as the K. And you can see that as you go towards lower momenta or larger distances, the coupling increases, so it is anti-screened. And now if you want to get asymptotic safety, you can basically combine screening and anti-screening. And you can do that in 2 different ways. One of them gives you a free parameter, and the other gives you a prediction. And let me first go through the case that gives you a free parameter. So this is what we call a relevant coupling. And a simple sort of toy model for the beta function would be that you have a leading order term that is positive, and then the next term, the quadratic term, being negative. And then the two cancel out at this alpha star. This is the fixed point value. But then you can see that because the leading order term is screening, that means that if you go towards slightly lower values than the fixed point, then quantum fluctuations drive you to even lower values, and they drive you further away from scale symmetry. And conversely, if you go to slightly higher values, then this quadratic term becomes important and drives you to even larger values, because this is an anti-screening effect. And so this means that even if you would demand scale symmetry somewhere in the very far UV, you could at any scale decide to depart from that with this coupling. And once you depart from scale symmetry to either lower or higher values by just a tiny bit, quantum fluctuations drive you away more and more. And so this means that even if you require scale symmetry somewhere in the very far UV, you still end up with a sort of whole range of couplings that you can achieve at low energies. And if you think about quantum gravity, that would mean you can achieve a whole range of couplings at the Planck scale. And so this is what gives you a free parameter. And now the opposite situation is if you just flip the order of the anti-screening and the screening term here, because then you have a situation where the signs are arranged in such a way that if you depart from scale symmetry by just a tiny little bit, quantum fluctuations will always drive you back towards it. And so generically, such a coupling, you don't have the freedom to move away from it, to move away from scale symmetry with it, because if you have fixed it to its scale symmetric value once, and then you would by hand sort of perturb it to be slightly away from scale symmetry, quantum fluctuations just drive you back to scale symmetry. And so for that coupling, you have no freedom to move away from the fixed point value, and this is how you achieve a unique value of the coupling at the Planck scale. And so this is where the predictive power comes from. And this predictive power persists to all lower scales. And an example for that is what you see here. So this is a sort of simplified space of couplings with just two different couplings that we call alpha 2 and alpha n, and there's a collection of 4 different fixed points. And you can see that there's the free fixed point that lies at vanishing values of the couplings, and you can see that there's a whole collection of renormalization group trajectories that depart from it, which means it has 2 relevant directions. Both of these couplings can depart from the scale symmetric value whenever you choose. And so both of them are free parameters, which means that if we wanted to know what the theory looks like in the infrared, we would have to do one measurement of alpha n and one measurement of alpha 2, and only that would actually pin down which trajectory we are sitting on. And then there are these partially interacting fixed points in magenta, and each of them actually has one relevant and one irrelevant direction. And you can see that nicely, for instance, with this fixed point here. So there's this green trajectory that is the only trajectory that departs from the fixed point. And you can see that in the other direction, you're actually attracted towards the fixed point. And so this means that you have one free parameter and you get one prediction, because alpha 2 and alpha n really become a function of each other. So if you start at the scale symmetric point in the UV, then you know that you have to be somewhere on this green line at all other scales in the infrared, even if you depart from scale symmetry. And so this means that if you measure alpha 2, you immediately get a prediction for alpha n. And so alpha n is the irrelevant direction that only changes as a function of alpha 2. And then there's also the fully interacting fixed point that actually doesn't have any relevant directions, because all of the trajectories from all directions approach it. And so if you would start at this fixed point here in the ultraviolet, you would have to sit at the scale symmetric point for all scales. All right, so this is the explanation of how asymptotic safety circumvents this problem of a loss of predictivity that we see in the perturbative approach to quantum gravity. Now, I'd like to talk in a little bit more detail about how the counting of these free parameters goes, and that is linked to the critical exponents. But before that, let me stop to see whether there are questions at this point.
Sorry, so the arrows on your phase diagram were pointing towards the UV then?
No, they always point towards the infrared.
Yeah, right. Okay. Yeah, thank you.
Yeah, because sort of the natural direction of the RG flow is that you have some microscopic physics, and that determines the macroscopic physics at larger scales.
Okay. Yeah, thank you.
All right, so then let me talk about how the counting of these free parameters goes, and that goes through the calculation of the critical exponents. So in this schematic plot here, you can see an interacting fixed point and its associated critical hypersurface. This is the hypersurface that consists out of the directions in which you can depart from the fixed point. And then orthogonal to that is this one direction, in this case here, that is an irrelevant direction where you're attracted towards the fixed point, and quantum fluctuations restore scale symmetry. And so if we want to know whether a coupling corresponds to a free parameter, so whether it's relevant, or whether it corresponds to a prediction, so it's irrelevant, we can actually just consider the neighborhood of the fixed point here. We don't need to consider this whole hypersurface. And so we linearize the beta functions. So we just write a generic Taylor expansion, and this leading order term, of course, the beta function at the fixed point that vanishes. And so then we have the first order term. So the derivative of the beta functions with respect to the various couplings, and then the distance to the fixed point value gi star. And we can solve that to get the coupling as a function of scale. It's given by the fixed point value. And then there's a sum over all of the eigendirections of this object here, which is called the stability matrix. The CIs, those are constant of integration. The VIs are the eigenvectors of the stability matrix. K0 is some arbitrary reference scale, and theta is the negative critical exponents. And so here you can see that there are directions that move towards the fixed point and other directions that move away from the fixed point. And so if you have a theta I that is positive, and then you go to scales k, which are much, much lower than your reference scale, then you can see that this term here blows up for the positive theta and a very low k. And so this means that this constant of integration, Ci, that becomes important in evaluating the values that couplings have at low energies. And so this constant of integration in this case becomes a free parameter. And that means that when you have a positive critical exponent, that will be a relevant direction or a free parameter. And you have the converse situation for a negative critical exponent, because then you can see that this term here just shrinks away under the RG flow as you go towards lower and lower k. And so this constant of integration can just take some arbitrary value. It will not enter the values of couplings at very low energies. And so there is no free parameter associated to this constant of integration in the case that the theta I is negative. Just a note in passing that one has to be a little careful when one is arguing with beta functions, because beta functions themselves aren't actually universal. So this means that they depend on various choices of how you do the calculation, of various choices of scheme, but they do contain universal information, which is the same across all schemes. And the critical exponents are one example of universal pieces of information. So you have to be a little bit careful with these objects, because the beta functions themselves, while not being universal, they contain these universal pieces of information. And depending on where you look in the literature, there can sometimes be a little bit of confusion because people argue directly at the level of beta functions when they shouldn't necessarily be doing so. All right. Now let me talk a little bit about the difference between free parameters at free and at interacting fixed points. And so we just take these linearized beta functions and the solutions again. And then we look at what the values of the critical exponents actually are. So at the free fixed point, they are just the derivatives of the beta functions evaluated at vanishing coupling. And now the important thing is that the couplings for which we look at the beta functions, those are dimensionless counterparts of the couplings. So generically, the couplings in a Lagrangian have a non-vanishing mass dimension. And in order to search for scale symmetry, we actually make them dimensionless. And we do that by just multiplying them with the RG scale to the appropriate power, where this d, g bar I, that is just the dimension of the dimensionful coupling gi. And now you can see that if you look at this dimensionless combination here, and then you hit it with the scale derivative to calculate the beta function, you will in particular also hit this k. And so if you then evaluate the derivative with respect to g and then set the coupling to 0, you'll actually end up with just this canonical dimension. And that tells you that at the free fixed point, it's very easy to do the counting of free parameters. You just look at the mass dimension of the couplings. Whenever you have a positive mass dimension, you have a positive critical exponent that corresponds to a relevant direction or a free parameter. Whenever you have a negative mass dimension, then that means you have a negative critical exponent. And so you don't have a free parameter, that is called an irrelevant direction. And then the tricky ones are those couplings that have vanishing mass dimension, because they could be either one, marginally relevant or marginally irrelevant. And here you need to evaluate the leading order term in the beta function beyond this canonical scaling term. Now the situation is somewhat different at an interacting fixed point, because there it's not only this canonical term from the canonical dimension that contributes to the beta function, that contributes to the critical exponent, but in general, because you evaluate this derivative at some finite value of couplings, there is also a contribution that is linear or higher order in the couplings. And now this contribution here, of course, can be of the same or of a different sign than the canonical dimension. And therefore, an interacting fixed point can be more or less predictive than the free fixed point, which can make it quite attractive. If it's more predictive, there's more predictive power to it. And that will actually be an important topic when we talk about the effect of quantum gravity on matter tomorrow. However, it also means that a priori there is no way to know the free parameters that a theory has, and you actually have to do calculations of the beta functions to do account of the free parameters. And so we'll come back to this question for gravity. And just this difference between free and interacting fixed point is something that you can also see in this plot that I already showed you, where the free fixed point has two relevant directions. So in this example, both of the couplings are actually marginally relevant. And then you have interacting fixed points both with one free parameter and also with 0 free parameters. All right, now let's talk briefly about mechanisms for asymptotic safety, and that will bring us towards asymptotic safety for gravity as well. Let me just stop to see whether there's anything more on the counting of free parameters that somebody wanted to ask before I continue. All right, so then let me talk about the mechanisms. The first one is where you take a perturbative beta function and you balance one loop versus two loop effects. So if you have a beta function where there's a one loop coefficient and a two loop coefficient, and then these hashes are the corresponding powers, depending on the coupling, those could be 2 and 4 or 2 and 3 or whatever. If you can achieve asymptotic safety in such a setting, if the one loop and the two loop, or actually the one loop against all higher order terms, actually cancels, and in this approximation where you just stop at the two loop term, the fixed point value depends on the one loop and the two loop coefficients, and you can see that you need appropriate signs so that this combination actually becomes real. And there's actually a very nice example of that in 4 dimensions. So many examples for long were quantum field theories in 2 or 3 dimensions that had such interacting fixed points. But in 2014, a nice example in 4 dimensions was found. It's gauge-Yukawa theories, where you can actually even strictly prove asymptotic safety if you're in the so-called Veneziano limit, where the number of flavors and colors becomes large. So here we are in a non-abelian gauge theory with the gauge coupling G, and then we are looking at this combination that is just the square of the gauge coupling. And then non-abelian gauge theories, of course, can become asymptotically free if they don't have too many matter fields in the fundamental representation present. However, if we then go to a setting with many matter fields, then the one loop coefficient, that is this B here, can actually switch its sign. So beta can become negative, which means that overall this coefficient becomes positive, and then you have lost asymptotic freedom. You can then gain asymptotic safety if the two loop coefficient is also negative. And that can happen if you also take Yukawa interactions in this model into account appropriately. So then you can get this asymptotically safe fixed point here at this ratio of one loop versus two loop coefficient. There is another mechanism that you can have for couplings which have a non-vanishing mass dimension, and that is a balance between the canonical scaling term and the quantum scaling term. So here we're considering a theory that is asymptotically free in its critical dimension, and the critical dimension of a theory is the dimension where the coupling is dimensionless. And so we assume that we start in this critical dimension, but then we go to d equal dc plus epsilon. Then the coupling acquires a mass dimensionality, and so the beta function no longer starts with the one loop term, but it actually starts with this term that depends on the canonical dimension that the coupling has now acquired. And then you can see that you can balance these two terms out against each other, again, if you have the appropriate sign. So for this, you actually need the one loop coefficient, this beta 1, to be negative. If that is negative, so if the theory is asymptotically free in its critical dimension, then you can indeed get an interacting fixed point. And example for that is, again, non-abelian gauge theories, this time without matter, in d equal 4 plus epsilon. And this upper graph here is from the epsilon expansion, going to, I think, 7th order. So this was work by Tim Morris. This alpha tilde is basically the same thing as the alpha before, so just g squared over 4 pi. And you can see that indeed there is an indication for an asymptotically safe fixed point here. And you can see the same thing with functional renormalization group techniques here. So this is the beta function, and there is an interacting fixed point that moves outwards as you increase the dimensionality towards higher and higher values. There's a quite interesting question in this setting, namely on the status of this theory in 5 dimensions, where these continuum techniques actually do give an interacting fixed point, but no indications for that is actually shown on the lattice in this most recent study here. So the status of the 5-dimensional theory is actually unclear. But we actually care about gravity, and for gravity, the canonical dimension is 2. So this means if you go to 2 dimensions, the Newton coupling becomes dimensionless. And then you can calculate the beta function in an epsilon expansion around 2 dimensions, and you get the leading order canonical term being positive, and then the next term, the term from quantum fluctuations, being negative, and that actually gives you asymptotic safety. And now, of course, it would be nice if we could just set epsilon equal to 2, but for that we would need few more terms in the epsilon expansion in order to do a reliable resummation. However, this result in the vicinity of the critical dimension, that already sort of motivates that gravity in 4 dimensions might be asymptotically safe. And so this now finally brings me to asymptotic safety in gravity. So the idea is that we basically have the same type of path integral that we start with in perturbation theory, but that the action is now not just the curvature term, but also higher order terms. And each of these couplings is a coupling that depends on the renormalization group scale driven by quantum fluctuations. And then the idea is that these couplings all assume an asymptotically safe fixed point in the ultraviolet, and the theory remains predictive at all scales through this mechanism that I explained, how couplings become irrelevant. And I would argue that this is the most conservative approach that you can take to quantum gravity, because it really stays sort of within what we already know about both gravity and about other fundamental interactions, because this approach just stays with the metric as its fundamental degree of freedom. And I would say that because this actually works well to describe gravity at low energies, we should only give up on the metric as the degree of freedom if this has really been shown to fail. And similarly, asymptotic safety uses the standard framework for the quantization, namely standard quantum field theory, that we also know works for the other fundamental forces. And so again, I think this is something that we should only give up if we can actually show that it fails. But of course, these statements here are very much something that one can, of course, discuss and view from different perspectives. So what we then actually need, if we want to see whether there is asymptotic safety in gravity, is an appropriate tool that works in 4 dimensions. And one of them is lattice simulations, where lattice simulations, for instance, in the framework of dynamical triangulations, they approximate space-time by discrete building blocks, and they then search for a point in the space of couplings where one can take this lattice spacing here, this sort of size of the building blocks, where one can take that to 0. And asymptotic safety actually allows you to take such a continuum limit, because it says that there has to be a regime where gravity becomes scale invariant and therefore doesn't care anymore what the sort of size of the building blocks is. And in order for that to be realized, there has to be a second order phase transition point in the phase diagram of these models. And indeed in CDTs, there is by now quite good evidence that there is a second order phase transition point. And the question now becomes whether or not you can approach this. However, most of the results for asymptotic safety actually come from functional renormalization group techniques. And so I'll introduce those techniques and then I will review the results that have been obtained for quantum gravity with those. So with the functional renormalization group, we can actually test the scale dependence or calculate the scale dependence of the couplings in a quantum field theory. And I'll first discuss the main idea of how the method works for scalar field theory, and then I'll briefly mention some of the complications for gravity. So it is important to highlight that what we work with here is the Euclidean path integral. And the reason we work with the Euclidean path integral is because we then can actually sort quantum fluctuations into a high energy and low energy, or sort of short wavelength and large wavelength, simply by looking at the Fourier modes of the Euclidean form momentum. And in this way, if we would do the full path integral at once, we would get an effective action for the expectation value. But if we do the path integral only for the high momentum mode, so if we only integrate out those of short wavelength, then we get an effective action that still depends on the scale k, that acts as an infrared cutoff. So it cuts off everything below the momentum scale k. And the way that quantum fluctuations below are cut off is by introducing a mass term into the generating functional. So if you have a mass term in the Euclidean action, then that actually suppresses quantum fluctuations which have that mass. And we don't want to suppress the high energy quantum fluctuations, we want to integrate them out. And so we choose this regulator term to vanish for the high momentum quantum fluctuations. But we do want to suppress the low energy fluctuations. And so for fluctuations which have Fourier modes smaller than, or Fourier momenta smaller than k squared, we choose this mass term to be non-vanishing. And in this way, we then get a scale-dependent or a flowing effective action that starts out being the microscopic action in the very far UV when k is very, very large, and then it goes all the way to the effective action at low energies. And in general, we can write this flowing action as just a sum over all possible interactions in the theory. So these OI are the possible interaction terms, and then we have the space-time integral over them. And then the size of these interactions is parameterized by the couplings, and those are the ones that carry the scale dependence. And so from the scale derivative of the flowing action, we get the beta functions. And now there is actually a closed equation that provides the scale derivative of the flowing action, which is known as the Wetterich equation. And I will not talk in detail about this right-hand side here. It's just a prescription how to actually evaluate the scale derivative that sort of structurally has a very similar form to a one-loop diagram in quantum field theory. The key thing to know about the method is that it provides a formally exact equation. However, this equation, if you write it out in beta functions, actually means that you have a tower of equations, of coupled equations for the beta functions of the different couplings. And because there are infinitely many couplings in the theory, it is an infinite tower. And in general, this is not something that you can actually meaningfully derive. And this is why one has to resort to approximations. And then, of course, the method loses its exactness. So the strategy is to then take into account only a finite set of equations here, or a finite set of interactions, or an infinite set of interactions, but of a very particular form. In such a truncation, you then search for a fixed point solution. If you find one, you then enlarge the truncation, and then you can step-by-step check whether the results actually converge. And if they do, or if they show apparent convergence, then you trust your approximation. And there are very many successful examples of the application of this method and this very strategy in particle physics or in statistical physics and condensed matter, many of which you can read in this recent review. And I would just like to highlight one example just to show you that this method, despite the fact that you need to make approximations here, this method nevertheless provides you with quantitatively precise predictions. And the example is the Ising universality class. So it's again the Ising model. And the number that we care about is a critical exponent. It's called nu here, and that's the scaling exponent of the correlation length. So it describes how the correlation length scales as you approach the critical temperature. And this scaling exponent has been calculated, for instance, with conformal bootstrap, but also a bunch of other methods. And the three numbers on the bottom here, those are functional renormalization group calculations in sort of successive orders of the approximation. So first in what is called a local potential approximation without derivatives, and then with interactions at second order in derivatives, and then going to sixth order in derivatives. And you can see this number agrees more and more with the conformal bootstrap estimate. And also this latest number here has actually a meaningful estimate of the systematic uncertainties. And so we now want to apply the same type of method in gravity. There's a slight complication that we have to overcome to do so. Namely, we need to be able to distinguish long and short wavelengths. And of course, we usually measure lengths by having a metric around. And of course, in quantum field theories on flat background, we do have a metric. But then metrics in the gravitational path integral are actually summed over. So which metric do we take? Well, the way out is to introduce an auxiliary background metric and use the background field method, where we write each metric configuration as this background field plus some fluctuation field that can become very large. So this is not perturbation theory. And in this way, we can still do the same path integral over all configurations. Excuse me. But we have this auxiliary background metric around with which we can write this term that distinguishes modes with large values of the covariant Laplacian. So those are the high wavelength modes, and distinguishes it from modes with low values of this covariant Laplacian. All right, so this was what I wanted to say about the method. Let me pause to see whether there are questions before I move on to some results for the last few minutes. All right, there don't seem to be any questions on the method. So let me talk about results. So I'll go sort of order by order in the approximation. I'll start with the Newton coupling or its dimensionless counterpart. So Newton coupling times RG scales squared. The beta function for that has this term 2G that comes from the canonical mass dimension. And then the leading order term that comes has a coefficient that is larger than 0 if written in this way, where the exact number depends on the regulator function. So you can see this non-universality or dependence on the scheme. You universally get a fixed point because this number is generically larger than 0. And the critical exponent in this approximation is always 2, independent on the regulator function. So here you sort of see this difference between non-universal and universal information in a beta function. And what this form of the beta function means is that the dimensionless Newton coupling increases. It starts out very, very tiny at LHC scales, but then it increases all the way up to the Planck scale. And once you hit this fixed point value here, then these two terms balance out, and it's no longer just this leading order term that wins. These two terms balance out, and you get asymptotic safety or scale symmetry above. Then we can include one further coupling that is actually even lower in canonical power counting, namely the cosmological constant. So here's the diagram of the Newton coupling and cosmological constant. You can see that there is an asymptotically safe fixed point in there. And you can see also that both of those correspond to relevant directions, because you can basically reach many different values of G and lambda starting from this fixed point. So both G and lambda correspond to free parameters. And so then there's the first non-trivial check of the theory, namely whether or not you can start at the fixed point and connect to a regime of classical gravity in the infrared. Now, in order to see whether or not that's the case, let's take a look at what characterizes classical gravity. So the classical regime is characterized by a constant dimension full Newton coupling, which means that the dimensionless Newton coupling scales as k squared. This is what I showed you in this previous slide here. In the classical regime, the dimension less Newton coupling scales like k squared. Similarly, in the classical regime, the dimension full cosmological constant is constant, which means that the dimensionless cosmological constant goes like 1 over k squared. And so if you combine these two, then this means that the product of G and lambda is constant in the classical gravity regime, which basically means that G scales like 1 over lambda. And this type of scaling you get on these trajectories here that pass close to the origin. They fit to a G is proportional to 1 over lambda scaling. And so there is actually a trajectory which realizes the measured values of G and lambda and has this behavior. So this would be the RG trajectory of our universe. So there's a first phenomenological test that asymptotic safety passes, and the fixed point in the UV is actually connected to classical gravity in the infrared. Now, moving on, with the sort of first non-trivial order in curvatures is the curvature squared. Those are the one loop counter terms of perturbative gravity. So where perturbative gravity starts to show signs of its predictivity problem. And there are actually three terms at this level. There's a Ricci scalar squared and a Ricci tensor squared. And then there is a topological invariant that is a sum of these two and then a Riemann tensor squared. And so if you build a truncation with Einstein-Hilbert plus these curvature squared terms, then you have in total 4 different couplings of local terms, namely Newton coupling, cosmological constant, and the B and the A. And then you have this one topological term. And it turns out that there's a fixed point which has 3 relevant directions, 1 irrelevant and 1 marginal. The marginal one is connected to this topological term. But the non-trivial thing really is that here you start to see how asymptotic safety is predictive, because in perturbation theory, you would just have 4 free parameters at this setting. In asymptotic safety, 1 coupling does not correspond to a free parameter. You can then again ask, can we use these 3 relevant directions to sort of connect to our universe? And one thing that you could want to connect to would be classical gravity plus Starobinsky inflation, which would be driven by this B coupling of the R squared. And it turns out that from this fixed point, there is this green trajectory that moves through here that actually realizes both the classical values of G and lambda, and also a value for B as you need it in order to drive Starobinsky inflation. The latter is not a must, so if you would like to realize inflation in a different way, or would just like to do without inflation entirely, then you can choose different trajectories where B takes a lower value so that you actually don't get into this inflationary regime. And then moving on to higher orders in the curvature, here I'm showing you work by Kevin Falls and Daniel Littim and collaborators. They've gone to significantly higher orders in the Ricci scalar, and then also in sort of combinations of Ricci tensor to some power. And these var thetas, those are minus the critical exponents. And so whenever these numbers are negative, this is where you have a free parameter. And you can see that there are just 3 of those. And then all of the other critical exponents are negative if you take this sign into account, meaning that you get lots and lots of predictions. Of course, these predictions aren't necessarily something that you can test very easily, because the predictions are predictions for the values of higher order curvature couplings. And those are not something that we currently, even in the strong gravity regime, really have meaningful access to. And so this is one of the aspects that we will address tomorrow, namely, is there a way of using the predictive power of asymptotic safety to make actually testable predictions and not just predict the values of higher order curvature terms, which we can't really test very well in observations right now. So just to close today's lecture, what we then really know so far is that it seems to be that asymptotic safety seems to have 3 free parameters. So this emerges both from these studies of all of the higher order Ricci scalar terms, but also it emerges from studies, for instance, including the Gorov-Sagnotti term or similar. So that means that there is quite a lot of predictive power. And also the interesting thing is that the values of these critical exponents, they are actually what is called near Gaussian, which means that they are quite close to the canonical dimension. And remember that if we were at the free fixed point, then the critical exponents would be exactly the canonical dimension. And so if we are at values of critical exponents which are close to the canonical dimension, then this means that this fixed point is not very non-perturbative. It's actually something that is by now being called near perturbative. It's not strictly perturbative in the sense that it's not strictly the free fixed point, but it's quite close to the free fixed point. And that actually also means that there is a very robust scheme how to choose truncations for reliable calculations, you choose truncations according to the canonical power counting. So terms which have a canonical high mass dimension are very likely to be irrelevant. And then if you've chosen truncations in this way, you then calculate the critical exponents to check whether the initial assumption was correct. And that in general is the case, as you can see in these calculations. And so this means that despite the fact that with the functional renormalization group, one has to make approximations, there is by now a way of how to make these approximations quite robust. And so in summary, there is now what I would call compelling evidence for asymptotic safety in gravity. There are some open challenges, for instance, the fact that the method that is used relates to Euclidean gravity. So strictly speaking, we should say that we have quite robust evidence for asymptotic safety in a quantum theory of space, not in a quantum theory of space-time. And so what I'll be doing tomorrow is asking the question, how can we make this into a theory that is not just about the building blocks of gravity, but also about the building blocks of matter? And also, how can we make this theory predictive by understanding what the implications for particle physics are? So with that, I'll stop for today, and I'm looking forward to more questions.
All right. Thank you very much, Astrid. Yeah, we have some time for questions. I would like to stop the recording at this point.